Hello! In this video, we are going to prove the following theorem. Let G be a group and suppose A is an element of G with order n. Then the subgroup of G generated by A consists of precisely the elements a to the power of 0, a to the power of 1, a to the power of 2, a to the power of n minus 1. Now, by definition, the subgroup of G generated by A is equal to the set of all elements of the form a to the power of k, where k is an integer. But the claim is, in the case where A has a finite order n, we can think of the subgroup of G generated by A as though it consists of precisely these elements. If we do a to the power of any other integer, then it's going to have to be equal to one of these guys. Now, in proving this theorem, we are also going to be using the division algorithm, which says the following. Let a and b be integers where b is greater than 0. Then there exist integers q and r such that a is equal to bq plus r and 0 is less than or equal to r is less than b. Okay, so now let's get into proving this theorem. To start out the proof, let's say that the identity element of our group is E. And for convenience, we're going to give this set a name. We're going to call it S. And we want to show that the subgroup of G generated by A is equal to S. And to do that, we're going to show that the subgroup of G generated by A is a subset of S, and S is a subset of the subgroup of G generated by A. Now clearly, S is a subset of the subgroup G generated by A. Because if we consider an arbitrary element of S, I'll call it P, well then, this means P is equal to a to the k for some integer k that is between 0 and n minus 1. And therefore, P is equal to a to the k for some integer k. So that tells us P satisfies the requirements to be an element of the subgroup G generated by A. And that's it. So if P is any element of S, then P is an element of the subgroup G generated by A. Therefore, S is a subset of the subgroup of G generated by A. So now let's show that the subgroup of G generated by A is a subset of S. To do that, let's consider an arbitrary element of the subgroup G generated by A. I'll call it P. From here, we want to show that P is an element of S. Now, since P is an element of the subgroup of G generated by A, this means that P is equal to a to the k for some integer k. But clearly, it is not necessarily the case that k is an integer between 0 and n minus 1. So we can't immediately say that P is an element of S. To show that P is an element of S, we want to show that P is equal to a to the r for some integer r. And r has to be between 0 and n minus 1. If we can show this, then that tells us P is an element of S. Now, because we want to show this, this hints that we should use the division algorithm. So we're going to apply the division algorithm to k divided by n. So taking a to be k and b to be n, well then, there exist integers q and r such that k is equal to nq plus r, and 0 is less than or equal to r is less than n. Now, since we're dealing with integers, to say that r is less than n is equivalent to saying r is less than or equal to n minus 1. Now, the claim is that p is equal to a to the power of r. And to see how, well, notice the following. We know that p is equal to a to the power of k. And we know that k is equal to nq plus r. So we can substitute k for nq plus r. But then, by properties of exponentiation, this is just a to the power of nq times a to the power of r. By properties of exponentiation again, we can re-express a to the power of nq as a to the power of n to the power of q. But since the order of a is equal to n, that means a to the power of n is equal to the identity element. So we can replace a to the power of n with the identity element. But in fact, the identity element to the power of any integer is equal to the identity element. So this is just the identity element times a to the power of r. And by definition of the identity element, this gives us a to the power of r. So this shows that p is equal to a to the r. And since r is an integer that is between 0 and n minus 1, that tells us p satisfies the requirements to be an element of S. And so we see if p is any element of the subgroup G generated by A, then p is an element of S. And that tells us the subgroup of G generated by A is a subset of S. So S is a subset of the subgroup G generated by A, and the subgroup G generated by A is a subset of S. And this tells us that the two sets are equal. And that is exactly what we wanted to prove. So this completes the proof. Now, this tells us that we can think of the subgroup G generated by A as consisting of exactly these elements. But it doesn't exactly tell us whether or not each pair of elements is distinct. For example, if we consider n equal to 6, well then in that case, the subgroup G generated by A is exactly the elements a to the power 0 through a to the power 5. But what this theorem doesn't tell us is whether or not every pair of elements in this set are distinct. For example, is it true that a to the power 3 is distinct from a to the power 5? And so our claim is the following. Still working with a group G, and still working with an element A in G that has order n, the claim is, given integers I and j, such that I and j lie between 0 and n minus 1, if I and j are distinct, then a to the power of I and a to the power of j are distinct. So, in proving this claim, we are going to be using the following result, which we have proven under the assumption that A is an element of G of order n. We have for all integers I and j, a to the power of I is equal to a to the power of j if and only if n divides I minus j. Okay, so now let's prove this claim. Now we're trying to prove if I is not equal to j, then a to the power of I is not equal to a to the power of j. And to prove this, we're actually going to prove the contrapositive. So we're going to prove if a to the power of I is equal to a to the power of j, then I is equal to j. So let's suppose a to the power of I is equal to a to the power of j. Well then, according to star, we can conclude that n divides I minus j. So I minus j is equal to n times some integer. I'll call that integer v. Now, we know that I lies between 0 and n minus 1, and if we take this inequality and multiply -1 through it, we get that the negative of n minus 1 is less than or equal to the negative of j, which is less than or equal to 0. And then, adding these two inequalities together, we get that the negative of n minus 1 is less than or equal to I minus j, which is less than or equal to n minus 1. Now, since v is an integer, we have either v is greater than or equal to 1, v is equal to 0, or v is less than or equal to -1. The claim is v is equal to 0. So let's eliminate the possibilities that v is greater than or equal to 1 and v is less than or equal to -1. So what goes wrong if v is greater than or equal to 1? If v is greater than or equal to 1, well then we know that I minus j is equal to nv. Well, since v is greater than or equal to 1, if we multiply n on both sides, we get nv is greater than or equal to n. So I minus j is greater than or equal to n, but that contradicts the fact that I minus j is less than or equal to n minus 1. So we've eliminated the possibility that v is greater than or equal to 1. Now let's eliminate the possibility v is less than or equal to -1. If this happens, well then, again, we know I minus j is equal to nv. But if we take this inequality and multiply n on both sides, we get nv is less than or equal to -n. So I minus j is less than or equal to -n, but that contradicts the fact that I minus j is greater than or equal to the negative of n minus 1. And just to unravel that a little bit, we know I minus j is less than or equal to -n, But we also know I minus j is greater than or equal to the negative of n minus 1. The negative of n minus 1 is equal to the negative n plus 1, and we know that the negative n plus 1 is greater than the negative n, so this implies I minus j is greater than negative n. This contradicts the fact that I minus j is less than or equal to negative n, right? So that's how we know that this inequality and this inequality contradict each other. So we've eliminated the possibility that b is less than or equal to negative 1. Because we've eliminated the possibility that b is greater than or equal to 1 and b is less than or equal to negative 1, we must have b is equal to 0. So then, I minus j is equal to n times 0, which is equal to 0. And then, adding j to the other side, we get I is equal to j. And so we've shown if a to the power of I is equal to a to the power of j, then I is equal to j. By the contrapositive, that means we have proven if I is not equal to j, then a to the power of I is not equal to a to the power of j. So this completes the proof. So that guarantees us that all pairs of elements here are distinct, right? And so yeah, that's pretty much it for this video.